What happens when AI models have to run on tiny wireless devices, squeeze into just 2 bits of memory, or shrink from massive foundation models into lightning-fast CPU-ready trees? In this episode, we explore 3 breakthroughs that push efficiency to the edge: a distributed transformer framework for ultra-low power MCUs, a spectral method that makes KV cache quantization surprisingly robust, and a distillation strategy that turns tabular foundation models into compact students without losing much accuracy. If you're curious how AI gets smaller, faster, and smarter at the same time, stay tuned. Let's explore the first paper, Going Beyond the Edge: Distributed Inference of Transformer Models on Ultra-Low Power Wireless Devices. The paper introduces CATS, the first end-to-end framework for distributed inference of transformer models on ultra-low power wireless MCUs, demonstrated on up to 16 NRF 52840 devices over a BLE mesh. Its core novelty is SumGather, a pruned all-gather primitive that broadcasts only selected activation columns, so cross-device communication is expressed as column-pruned all-to-all exchanges. This simultaneously reduces bandwidth, per-device activation RAM, and flash footprint. CATS partitions multi-head attention, along attention heads, and feature columns, so each device computes local layer normalization, Q, K, V projections, and head-wise attention with minimal inter-device traffic. To handle packet loss, CATS adds message dropout, MD, which trains the model under realistic wireless loss patterns across all layers rather than a single split point. On 4 time series forecasting benchmarks: ETT, H2, ICD, London smart meters, and traffic. SumGather preserves prediction error while normal pruning degrades accuracy as communication savings increase. Quantitatively, SumGather cuts communication volume by up to 90% and per-device activation RAM by 67.5%, compared with unpruned DTI, and MD reduces the test error increase under 10% message loss from as much as 200% to 23.6% across datasets. In hardware experiments, CATS executes a 1/4 million parameter vision transformer, about 14 times larger than what a single MCU can run. With 90% pruning, latency improves by up to 4.68 times on the residual block and 4.37 times on the attention block, while the 1/6 device system remains communication efficient on a 2-hop wireless mesh. Let's explore the second paper, Oscar Offline Spectral Covariance Aware Rotation for 2 bits, KV cache quantization. Oscar is a 2-bit KV cache quantization method that replaces data-oblivious rotations with offline, attention-aware spectral calibration. Rather than optimizing raw KV reconstruction error, it estimates layer and head-specific covariance targets from a small calibration pass. Query covariance QIMQ for keys and score-weighted value covariance VINSS SV for values, where S is the attention matrix. It then builds fixed rotations, RK equals UQHH PBR and RV equals USHH PBR from these eigenspaces, combining PCA, Walsh-Hadamard mixing, and bit reversal permutation to equalize importance across channels and reduce outliers before asymmetric INT2 quantization with per-token percentile clipping. A key theoretical result shows these covariance targets minimize a frozen error surrogate under diagonal residual assumptions. In production, Oscar is implemented in SGLang with fused Triton kernels, paged KV cache compatibility, BF16 protection for sync and recent tokens, and packed 2-bit history storage, so it fits standard long contact serving pipelines. Empirically, on 32K, generation evaluations over AME25, GPQA Diamond, Human Evil, LiveCode Bench v6, and Math 500, Oscar at 2.28 bits per KV element cuts the BF16 accuracy gap to 3.78 points on Quen 3.4b, Thinking 2.507 and 1.4, 2 points on Quen 3.8b, while naive INT2 and Quarat INT2 collapse to near 0 on these reasoning workloads. On Quen 3, 3.2b, and GLM4, 7 FP8, it is essentially on par with BF16. On Ruler Naya up to 128K tokens, Oscar stays robust where rotation-only INT2 fails, and system measurements show about 8 times lower KV memory, up to 7 times higher throughput at large batch sizes, and up to 3 times faster batch size, 1 decoding versus BF16. Let's explore the third paper, Pocket Foundation Models Distilling TFMs into CPU-ready gradient boosted trees. Pocket foundation models shows that tabular foundation models such as TabICL-v2, TabPFN-v2, 6, Limix, and Orion MSP can be compressed into CPU-ready, gradient-boosted tree students without most of their accuracy loss, but only if the teacher is labeled out of fold. The key novelty is that in-context learning teachers leak labels when they score examples from their own training context, collapsing soft targets to near one-hot vectors. Stratified 5, fold out of fold labeling restores usable interclass structure for distillation. Across 153 classification datasets from Talent, OpenML, CC18, Tabzilla, and Tabarina, TabICLV2 XGBoost reaches 0.882 macro mean ROC AUC, retaining 96.5% of the teacher's AUC while running in 1.9 milliseconds on CPU versus 151 milliseconds on GPU for the teacher, a 79 times speedup, and 38 times to 860 times across all teacher-student pairs. This student beats a tuned CapBoost baseline on 51% of datasets with a Wilcoxon p-value of 0.0008. The strongest teacher always produces the strongest student, so teacher ranking transfers exactly to student ranking and gains concentrate on low-dimensional tasks with 21 or fewer features, where distillation improves CapBoost by 0.011 AUC on average. Above 21 features, the gain falls to 0.001. Multi-teacher averaging helps MLP students by plus 0.006 AUC, but is negligible for tree students, and distillation fails when the teacher itself underperforms CapBoost on high-dimensional data. That's a wrap on today's AI paper highlights. Thanks for watching.